Welcome. My name is Martin Whitworth and I represent Campden BRI, which is an independent company in the UK which provides scientific and technical services for the food industry. This presentation is part of the MUSE-Tech project in which we're a partner. MUSE-Tech is funded under the EU Framework 7 programme, and it concerns the development of a prototype sensor for online measurement of food processes. And Campden BRI's involvement has been evaluation of the sensor for application to bread production, which is the subject of this presentation. So our objectives are to identify what the potential is for improving control of baking processes through measuring some additional properties that aren't currently measured, and to assess whether the particular device built in MUSE-Tech is capable of making those measurements. For those who are not familiar with bread baking processes, this is a schematic. We have a batch mixing operation at the start, and then that feeds dough pieces through several other continuous stages. MUSE-Tech works within the framework of process analytical technology, which identifies a few particular terms, one of which is critical quality attributes. So these are properties of the raw materials of the product that you're seeking to control. Within a bread process, the final loaf quality includes things like the volume of the loaf, its structure and its firmness. Raw materials will also be assessed. Flour quality in particular is important, so there's a number of properties that will be included in a specification. And there are several things that we can identify through the course of the process. So the rheology of the dough as it comes out of the mixer, and for example, coming out of the prover, the height of the dough is critical. And once you've baked it, the external colour is something that matters. Another term identified in process analytical technology are critical process parameters. These are things that we can control and measure in the process. So in a baking process, for mixing, it would be how long or how much work you put into the dough. And in some types of mixer, you can also control the pressure in the headspace. For the prover, it's things like temperature and humidity, and for the oven, it would also be temperature and temperature profile in a bit more detail. Within the MUSE-Tech project, we felt that the sensors we have would be relevant for the mixing and the final proof processes, so that's what we will focus on. And we've picked out a couple of measurement targets that we think are relevant in these processes. So within dough mixing, it achieves several functions. Obviously, it combines the ingredients, and it's the stage at which the flour becomes hydrated by the water in the recipe. We also include gas bubble nuclei at that stage, which will expand to form the bubble structure of the bread. And we also mechanically develop the gluten to give it the right rheological characteristics. And our measurement target here was to take near-infrared spectra of the dough online as it mixes, and to see whether those can tell us something about the state of the dough to help control the mixer. We also planned originally to measure the oxygen in the headspace, because oxidation is an important process here, but I won't be reporting on any measurements of that. And within the proof process, this is the stage at which the dough ferments with the yeast in it. It's placed in a warm, humid chamber to encourage that to happen. And fermentation produces carbon dioxide, which expands the bubbles and gives us the volume of the dough. And we felt it might be interesting here to measure the volatile products that are produced by fermentation and to see whether those would be useful control variables. The device that has been built within MUSE-Tech is a prototype multisensor built by some of the other partners in the consortium. It combines three novel photonic technologies. One of these is a distributed temperature sensor, which was built by the Institute of Photonic Sciences in Spain. Photoacoustic spectroscopy, this is a sensor built by Gasera in Finland. And we have a spectrometer. It's capable of visible and near-infrared measurements. For our application, we'll use it in NIR, and this was built by VTT in Finland. And all of these have been integrated into a single device with a common control and data logging interface, which was done by Peacock technology. And the benefit of the device is that it can be configured for lots of different applications. I'm assessing it for baking, but other partners in the project have assessed for other applications. So first I want to talk about NIR spectroscopy, which is one of the methods that we have built into the sensor. A little bit of background on this. My colleagues, the reference shown at the bottom, did some research about 15 years ago with a commercial NIR spectrometer that they mounted to take spectra from a dough mixing in a small laboratory mixer. And they identified that the bands within the NIR spectrum changed during the course of the mixing in a way that enabled you to identify the optimum time of mixing. So within MUSE-Tech, we wanted to take this a stage further and to see whether we could use the novel low-cost spectrometer that's been built in the device to make similar measurements, and whether we could scale this up to work with larger mixers. The spectrometer built by VTT for this thing is an 8-channel spectrometer, and usually those sorts of things are expensive, but they've used a new approach that enables it to be built at a much lower cost. And it's versatile and can be configured to different band spacings and different band ranges. We're using a fairly wide range of NIR spectra for these purposes. And we initially did some trials with some flour samples just on the bench in some cells to see how the instrument performed under well-controlled conditions before applying it to doughs. And this is something that NIR is usually pretty good at. So we took 100 samples of diverse flours with reference analyses as well to see whether we could build calibrations for them. And we made some static measurements of those flours. You can see some examples of the raw data that we get from the spectrometer in the graph. This particular type of spectrometer, the way it works means there are certain discontinuities in the raw data, but we know where they are, they're in fixed positions, so we should be able to correct for those. We also take a reference white and normalize for that, which is standard procedure, and so this shows the actual absorbance spectra of the samples. You can see that some of those discontinuities still remain, but we know where they are and can avoid them. There's also some noise towards the longer wavelengths, which is where the signal was fairly low and the spectrometer is less sensitive there. But we can still see the main bands that we had identified in the previous work, which gives us some confidence that we might be able to apply it to mixing. So moving on to that, one of the issues that we had of scaling up to a large mixer is getting enough signal back to be able to measure a spectrum. We've built a separate probe that is sealed for use with the mixer, and to deal with this power issue, it was designed with high power illumination, so there's a focused light source aiming down into the mixer. We've mounted it over the lid of our mixer, shining down through a quartz glass window, which is transparent to NIR over the full wavelength range. But unfortunately, when we did these trials, we found that the path length that we were dealing with was still too long for us to get a signal, despite our efforts to deal with that. We also have an issue that if we want to get high power, then we can get that by focusing the light beam down. But that doesn't work so well when you've got a dough that's moving around, because it's only going to be in the light beam some of the time. So these are conflicting demands, and ultimately that was a limitation. The previous work we had done used a spectrometer with a fiber optic bundle, but the nature of how this new design works, and although it's cheaper, it is restricted to only a single detection fiber coming in. So again, that limits sensitivity. Could be quite good for many applications, but for this one, we need quite a lot of sensitivity, and it doesn't seem to be an appropriate design for this, so we would have to revert to traditional approaches. With the other technologies in MUSE-Tech, though, we had somewhat more success. So the second one I want to talk about is a distributed temperature sensor, which was built by ICFO in Spain. And this is an optical method of measuring temperature. We have lots of temperature devices around which are electronic in nature, resistance thermometers and the like. But this uses a purely optical, non-electronic sensor. And you can have several of these sensors mounted around a factory and just connected together with optical fibers. So the entire measurement is done with light, with no electrical signal. benefits that I see of this is that it's a robust system that you can easily install in a factory. You can run it over long distances, and you don't have to worry about electrical interference and the like. And you've also got less cabling, because you can actually daisy chain a whole load of these sensors together along one fibre optic. The graph you see at the bottom is the signal that comes back to the detector. You see pulses or peaks at several individual wavelengths. Each one of those is identifiable as coming from one of the sensors, and small changes in the wavelength that you get there will tell you what the temperature is at that sensor. So this is what distributed temperature sensors are. It means you can make measurements at multiple places around a factory. We've done some trials of using this to measure temperature in a prover. Initially, on the left, we did some trials in a laboratory scale prover at Campden BRI, and we mounted 8 probes at different points around that prover. And then we've done some scale up with a commercial scale prover that you see on the right. The box was mounted outside the prover, and the fibre optics were strung into various points inside the prover. And this is demonstrating the real application of the system. That it's quite a large prover, and we've got long lengths of fibre optic. These are some of the results from the laboratory trials. For laboratory 1, we were able to do tests at various different temperatures to see what the performance was. And I've put 3 different temperatures there, just showing records over the course of a few hours. The measurements at the 8 different positions are all slightly different. This is to be expected. We don't have completely uniform temperature within a prover. You can also see some periodicity in the traces, and that's because there's thermostatic control on the prover, so this kicks in and out at various intervals. An interesting feature is that at higher temperature, it has to kick in and out more rapidly, so you actually see a higher frequency signal. And these are similar records done from the production trials. This is over a longer period of time. This is actually showing a record over 11 hours. So this was for continuous production of one particular sample. And you see the same sort of issue, that the temperature isn't exactly the same at all points in this large prover. You also see the periodicity for a controlled system. And interestingly here, there's a slight phase shift between the measurements at the different positions, presumably because temperature changes made at one point take a little while to work their way through the full volume of the prover. So a very useful device for recording temperature at multiple positions and doing it entirely optically. And the third technology that we have in the MUSE-Tech multisensor is photoacoustic spectrometry. This is an optical technology for measuring concentrations of gases and volatiles. For the baking application, the device was configured to measure water, because we have humidity in a prover, carbon dioxide and ethanol. Both of those are gases that come from the fermentation process. We first of all did some validation using controlled mixtures of gas in the laboratory and making some comparisons against reference probes for each of those individual gases. And then we moved on to trials in the prover, and you can see some sampling tubes, the little blue tubes you see in the picture at the bottom, running into our laboratory prover and going out to the MUSE-Tech sensor. And the method is that the gas is sampled along those tubes, comes into the detector and is measured there. So these are the results for the reference measurements, and you can see that there is good agreement with the reference measurements for all 3 gases. There's some scatter, so it's not necessarily a perfect thing, but it is sensitive to all 3 of those gases, and this is one single sensor that's able to measure all of the gases together rather than having to use 3 different ones. The ethanol here you see saturating, but these reference tests were done at very high concentrations of ethanol, way above what you'd actually see in a prover. So that was initial validation that convinces us we're measuring the right thing, and we then move on to trying to apply it in a prover. And in the laboratory prover, we were able to do some variations. So we tried with the prover empty, full of doughs, or half full of doughs, and also at several different temperatures. We also measured the height of the dough, which you can see that in the graph, height is a function of time for all these conditions. So you can see that the dough is rising, and the red curves are the ones done at higher temperatures, and the dough height increases faster This is because the fermentation rate is higher at greater temperature. So we then look at the gas measurements. First of all, the humidity. This was, of course, being controlled in the prover at a constant setting, so we're seeing a fairly flat trace. We do see greater signal for the higher temperature measurements, because although we're keeping the relative humidity the same, at higher temperature that actually represents more moles of water vapor. So that explains why we're seeing a temperature effect. We would expect the effect to be greater than we see, but nonetheless we're picking something up. For carbon dioxide, we also see no variation. That's a bit of a surprise. We would expect elevated levels in the prover. We're not fully sure what's going on there. We think possibly we're just recording ambient and it isn't long enough for the CO2 to work its way down the tube to the detector. Ethanol is much more interesting. If you look at the top right graph, which is the reference probe, you can see that from putting the dose in the prover, the concentration of ethanol is continuing increasing over the course of proof, and we proof for about an hour. And at higher temperatures, we see a greater rate of increase, which is consistent with the greater rate of fermentation we'd expect. And also, if we put more dose into the prover, then unsurprisingly, we generate more ethanol. The photoacoustic spectrometer, however, is limited on sensitivity, so we're getting a much lower signal here. And it's only for the various highest concentrations that we got with the reference probe that it's actually detecting it. So it's showing a similar behavior, but only at high levels. And again, we think this may be an issue with the time it takes for the ethanol to work its way along the sampling tube and into the detector. That isn't so much of a problem when we go to a big commercial prover, though, and this has worked much better. So here you see traces over the course of 24 hours, both for the reference probe and for the photoacoustic spectrometer, showing the ethanol concentration in the commercial prover. And here we're running it continuously. There's a nice concentration of ethanol in there, and we get a good signal. And we're on a continuous run, but where you see the vertical lines on the graph, there were temporary gaps in production at those points. And for most of those, you can see that there was a response, that there was a dip in the ethanol production that followed a gap in that. So it looks like the thing is responsive. Ethanol concentration isn't normally measured in provers, and so this is quite interesting to see that it is potentially a useful variable that can tell you something more about your process. So something that could be built into control systems perhaps in the future. So that's the final data I want to present. In conclusion, we have built a multi-sensor device within the project, and it's been configured for bakery processes, and we've assessed several applications of that. For near-infrared spectroscopy, we were hoping that we would be able to measure something useful about dough in a mixer. Works nicely for flour, but unfortunately for the mixer, we're struggling for signal strength with this particular design of spectrometer. But for measurements in the prover, we have demonstrated very nice measurements of temperature with an optical approach that doesn't have all the issues of cabling that you'd have with electrical methods. And we've also been able to measure the gases that are present in a prover. In a laboratory, we were struggling for sensitivity, but when we use a full-scale production trial, it works much better, and we can see some changes in response to variations in production. Okay, so that concludes the video. I hope you've enjoyed watching it.